Okay. So in the second part of the course, we're going to describe some methods. There's the first one for face detection. So that's the one I mentioned that you probably have seen in your camera phones, which detects a face with a small square. This is very, very commonly used, and it's one of the state-of-the-art methods. There are, of course, alternative, implementations of it, but I'm going to describe the main ideas. So I think it's cool to know that when you use a camera, it's actually this algorithm that you know that's being used. Then I will describe some facial landmark detection models. So basically models that can help you track points on the face, such as the outer parts of the lips. Those then, once you have that, you can use to detect facial expressions or other kind of signals. And I will do a quick introduction to computational neural networks. I also want to introduce a bit the first homework. So maybe I'll skip a bit at the end so that we get some chance to talk about it. Right. So face detection. What do you think? Is it easy? There's a face in this image. Can you see the face?
I can see this.
You can see one?
Yeah.
Which corner?
This one. Oh, yes.
Here?
Yeah.
There's a face.
All right.
So it's a very hard problem. The top right corner. I think I don't have the image, but there's a very, very cool image of a 360 camera put in the middle of a football field, and they try to detect faces, and we can see all of them, but none are detected because it's so hard. But there's an algorithm that has been developed, I think, about 10 years ago, and now it's been incrementally improved, and that now it's so fast and so efficient that you find it in basically every kind of hardware that detects faces. So the basic idea of this facial detection technique is, well, there's no way around it. We need to search everywhere. So we need to slide the window everywhere in the image and search for a kind of face. Problem is, you have many kind of positions, you have many scales. If you have a very large image, it becomes a very complicated problem. So the main idea is we need to go very fast and we need to discard all the ones that are clearly not faces very fast. And then we can maybe go deeper and say, oh, well, maybe this is a face, I'm not entirely sure, let's go deeper. And now we can do more processing. But the basic idea behind this algorithm is make sure first that we remove lots of negative candidates. This is not a face, not a face. So there are three key ideas. One is to use features that are very, very fast to evaluate. The second one is to use a kind of feature selection method to use a very, very low number of features, at least for the first passes, so the passes that discard all the faces. And the third one is the one I introduced, which is you have actually successive passes over the different windows on the image that are successively more complex. And the first one are so simple that you can do them in a nanosecond. So I introduced those features called Haar filters, which are rectangle filters. If you have an image, let's just say black and white for now, but you could just, if you have an RGB, you could just map it from black and white. The really simple idea behind these kind of features, you just add the pixel values in the white area and you subtract the one in the dark area. So it's kind of an idea of the contrast between what you have in the white area and the black area. So in which part of the face can this really help us? Well, to give you an example, you can use it here to detect the difference between the forehead and the eyes. Or you could do it with maybe the nose and the sides of the face and the eyes. So why is it so fast to compute these kind of things? Do you have any idea? What can we do to compute in an image like super fast with the least amount of references and computations?
Gradient change? Gradient change? I mean, intensity range compared to the neighbors?
So that's not what we use. But,
you use pre-calculated image like integral image, something like that?
Which I understood.
Use pre-calculated image feature like integral image, so that you can like compare value of area with pixel-wise.
Exactly. So what you do is you actually pre-calculate the value of this rectangle everywhere on the image. So if you take one point here, you calculate the value of the top left rectangle, the area. And if you have this, so this is very fast to compute on just one pass on the whole image. You do it once and then it's done. And then you just have this database of for every point of the image, you have the value of the rectangle on the top left. And then it's actually pretty easy to compute a new value for any rectangle, because you can just take this value here, plus this value here, minus this value here, and this value here. Does that make sense?
Yeah.
So you can just take any rectangle in the image, you just have to take 4 references, and so for your CPU, it's actually a very, very trivial operation. And this is done so in nanoseconds. Still, there's a problem remaining, is that you have many, many kind of features. Even for a tiny, tiny image, you can define many kind of rectangles. So feature selection is a process of selecting which are the features that will be the most useful for a classifier and for detecting faces in our case. So which one of these are the most useful? Well, the idea is for this face detection algorithm, can we create a good classifier with just a tiny amount of features? So in this case, the answer is actually no. But what you can do is combine multiple sets of features one after each other to create a more and more efficient algorithm. And this technique is called boosting. So boosting is a technique used in machine learning to combine different classifiers into one. So they can be all pretty bad, they can have weak scores. But the idea is that if one classifier is good at least identifying some kinds of faces, but very bad at all the others, well, you keep it, and then you just take a classifier for another part of your whole feature space, and then another, and another, and another. So what this does is combining what's called weak learners into one strong learner. So in boosting, you have multiple rounds. The first one, you just take one classifier, which doesn't even have to be that good, and then you add another one to it, and another one. Yes?
What's the difference between boosting and the ensemble methods? And I mean, the ensemble methods would be like decision tree and a random forest kind of thing.
So the thing with boosting is that you could actually use, it's more like a framework. You could use one decision tree as one learner,
Okay.
and add another one to it.
Okay.
So boosting is a general scheme. Whereas the decision tree, for example, is one kind of classifier. And it could be a weak one or a strong one.
Okay.
So one thing you could do is actually combine multiple decision trees. You have one to detect one kind of faces, it does really well on one part of your feature space. Then you create another one that's much better on another part of your feature space.
Yeah, but that would be like an ensemble method. I mean, a random forest is a group of trees.
So, well, yeah. I think the thing with random forest is, so the name random is that you actually select every kind of tree has a different kind of set of features that's absolutely randomly selected. In boosting, it's not randomly selected. You first create your best tree, the best tree that you can, and then you look at the examples that were not, accurately classified. The ones that you got the most wrong, and you take those ones and you create another tree with it. So the difference is that it's not random. However, I think you have a good intuition that it's kind of similar, in that you take multiple passes and you separate your data sets into different kind of smaller subsets. But I'm not an expert in this kind of methods, so I wouldn't know. So to give you an example, this is a kind of, I don't know, just a total data set you have. Red is yes and blue is no. And you have two features, the x-axis and the y-axis. Let's say you create one classifier which separates your feature space like this. So it's pretty bad because it's got too, I mean, you have more nodes here than you have nodes here. Maybe it's a bit, 60% accuracy, I don't know. Maybe you can calculate that. But it can definitely do better. The idea is once you have defined this first weak classifier, you improve the importance of some inputs of your data set to create a second classifier. So the one that were really wrong here. And then you create another one using this new data set with different weights. This classifier also does quite bad, although at least on the right part it's completely right. You do another classifier, etc., etc. And then you end up with a combination of classifiers that if you combine them, it's actually much better. And all these classifiers can be quite simple. So that's the general idea of boosting. Finally, the third idea that is used in the Weill-Jones algorithm for face detection is the attentional cascade. So that's the idea I told you about of first trying to discard as many as we can, as fast as we can, of the non-face windows. And then we take the set that are still here. We also try to discard some as fast as we can, etc., etc. So we have a first classifier, but we're going to talk about this kind of graphs. As Professor Scherer talked about this kind of graphs, I don't remember, the receiver operating characteristic graphs. So this is the kind of graph you use in machine learning to describe how well the classifier performs, basically. And it basically plots the rates of true positives on this axis and false positive. So what you want is basically to have 0 false positive and 100 true positive. So that means you detect all the good examples, you classify them correctly. So you want that curve to be really on the top left corner. So basically what you do in this with this method, the attentional cascade, is you build one first classifier, which is not that way. Then you add another one after it, combine them, and you have a much better performance and a better performance, etc., etc., etc. The idea is that all these classifiers have to be very, very fast. Right, so I don't think I have a slide on that, but it turns out that the first classifier on this method only has 2 features, which is one that is horizontal on the forehead and the eyes that I showed you, and one vertical on the nose and the side and the eyes. So just doing that, you actually remove 99% of the non-face windows with a very strong accuracy. So are there any other questions on this method, on this technique? No? All right. So this is really state-of-the-art classifier for detecting faces. There are obviously extensions. But if you use any kind of phone, that's the one you have. So now that you found a face in your image, and you narrow it down, you cropped your image, and you have a face in a small and nice square or rectangle, how can you detect facial landmarks? How can you detect maybe the tip of the nose, or the contours of the eyes, or the eyebrows? So one technique that I will introduce is the active appearance model. Active appearance model, basically they try to split the problem into 2 things. One is the shape of the face, and the other one is the texture of the face. And to use these 2 kinds of information separately, to try to map your input image into a set of points. So the first part is you get a data set of all these example image. And if you see it in the back, you have small points on many different parts of the face. So you have 1 point here, 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 on the nose, on the lips, on the eyes. And those are the feature points that you want to track in any kind of good image. So you have this data set along with maybe thousands of images, and they all have been labeled manually with these points. The first thing that you do is a process called shape analysis. So there are techniques called, for example, Procrustes analysis. Basically, all these images have the same kind of shape. they are obviously different, but they all have the same structure. And this kind of analysis will be able to tell you, well, this face is, I mean, if they are all the same shapes, well, then this one is a bit larger, this one is more rotated, so they're all normalized. Then you can actually plot for each point, you can plot them on one graph for all these kind of normalized shapes. And you see there's still a lot of variability, of course, because we have different faces. The next step then is to do what's called a principal component analysis, which is a technique that tries to reduce the number of dimensions of variation if you're in your data set. For example, so many faces, I don't know, they can be larger here, here, but maybe they're all larger at the same time, let's say. So you have different dimensions that are basically they vary in the same way along those dimensions. The PCA technique, so principal component analysis, allows you to find those components of variations that are the most, let's say, the most common in your data set. So once you have that, you can take your mean face and you have three variation, let's say, dimensions, and you can, let's say, just take any value for these different variation components. So maybe I want to make my face, any kind of face a little bit larger, a little bit taller. And you can create any kind of face with just three variables instead of maybe the 61st points you had on the face. So once you have this model of the shape of your facial points, so how they vary together, basically you crop the different images of faces and you just take texture in your shape. The idea of the active appearance model is to, well, first you warp them to the mean shape, so that means you, depending on the kind of scale and orientation of that particular face, you warp them to match the mean face. And you do also a PCA, a principal component analysis, on the pixel values, every pixel in your shape. What that will give you is a mean texture, so that's probably not a real person, but that's like the average texture of your data set, of the faces of your data set. And then same thing, modes of variations, basically. So what's very interesting when you have that is you can, if you take a parameters for all of these variations, you can create lots of different kinds of faces. Maybe not all of them will look very realistic, but you'll have, just by manipulating a number, you can create a face. And so this is a mathematical representation of that model. So you have two components. One is the shape, the parameter, which is, you have the mean shape as 0 with different mode of variations of the shape. And the second one is the appearance, which is the texture. So this can be used then to fit any kind of face. If you train your model to detect these modes of variation, you can try in real time to detect facial points on the face. So you'll see in many of these examples, like here, for example, on the chin, it's actually quite lost, and there's a lot of how do you say? There's a lot of warping. There are lots of artifacts. But still, it's one of the first methods that was developed, and it's already quite good. So another method I want to introduce is called constrained local model. So it's in many ways a very similar kind of model, but it does one thing to improve, which is not try to model the whole face. As you can see in the active appearance model, you model the whole texture. And intuitively, maybe the color of, I don't know, the cheek will be kind of stable, the whole cheek. And maybe you do not need that to detect other points that are quite far away. So what the constrained local models try to do is only model the texture that is very close to those points that you're trying to track. For example, here the eyebrow on the top left, you only try to model a very small window around this instead of the whole face. So constrained local models use image templates. So I introduced them a bit earlier. So those are tiny images that are representative of the kind of thing you're trying to track. So let's say you have, I don't know, 1,000 face images, and you've all labeled them for the tip of the eyebrow here. Well, you just sample a 4x4, 8x8 template around it, and you average it, and that's your mean template for an eyebrow, for a tip of an eyebrow. So, what the constrained local models try to do is, once you have the face, that you have just a general window of the face, you already have more or less an idea of where the eyebrow is, right? So the eyebrow is more or less in that big square. Well, what you do is you define your search window for the templates here instead of on the whole face. And you do a search window for all of the feature points you have. So you're going to look for the bottom of the chin on this whole square. And you're going to try to map your the feature templates that you have on all these points. What this gives you is a response map, basically. So on this whole window, you have a more or less high value, and that gives you a sense of, well, we think maybe the bottom of the chin is more on this point rather than this point. Right, so to give you some example. On this face, we have different kind of features we're trying to track, and if you do on this search window for the tip of the left lip, this is the kind of response map that's trying to match this your left lip template. Right? That's what you will get. So you have darker values here. Maybe that means that on this corner, well, it's really not likely to be favored. However, this is very light, so that means there's a light value. It's very similar to your examples of what a left lip is. So that means probably this is the most likely point for the left lip for that character. And you do that for all your different feature points. So, well, these are the results from the paper that introduced the method, saying that you don't need actually that many examples. So, in order to detect one actual point, the authors of that method actually propose to use logistic regression. So, to find really basically a smaller set of a smaller area of optimal location basically for your feature points. Now once you have that, there still remains a problem, is that you could have great locations for your local points, but you could have local variations that in the end your shape will be a bit distorted, right? It could be, maybe it will be a bit ragged. It will not look, maybe locally the points are really well aligned, but actually when you look at the whole face, it's not much like a face anymore, it's a bit distorted. So this is why it's called a constrained local model. The local models are the local search for that point, for those points, and the constrained part is basically a process that you do in the end to try to find the optimal, you try to optimize the shape of the face, the global shape of the face, such as like in the previous method, and also the local responses. So you have all those local responses maps, you try to find the best point there, and at the same time, the best points, the best combination of points that does a thing that resembles the best face. I don't know if that makes sense. So you have two parts, which is one, you look for those feature points in local search windows, and the second one is you try to optimize the global kind of appearance of the face. So,
what's a PDM?
Sorry?
What's a PDM?
The PDM, I think it's a point distribution model, which is in this kind of, in this method, is the way you describe the shape of the face, basically. So that, yeah, the point distribution model. So for example, you have various kind of shapes here, and you try to match something like this, so it's kind of continuous and smooth. If you had feature points that would be really ragged like this, then you would say, well, this is really good. And so you would be, your optimization strategy will be will say, well, I will maybe not take the optimal local response, but at least the point distribution model is a bit more, it looks like a face. So the kind of tools you'll use if you want to do facial expression recognition for your projects, we'll recommend a tool called OpenFace, and it uses this technique actually to detect facial points. So you'll be able to see how it works in real time. Maybe I'll do an introduction on the next discussion. All right, so once that you have these points tracked, and you also have these other global features that I introduced before, how do you recognize a facial expression? So one method is that was proposed, and we also recommend you use that, even though OpenFace now does also actually need recognition, so you don't need to use it, but we used to do it, so that's why we still have this one. One method that was that's kind of the state of the art facial expression of emotion recognition technique is to combine those two tools I introduced. So first you have a facial detection algorithm, so that's the Bioagent method. Then you track the feature points. And then using those feature points you extract actually local other features that try, maybe if the eyebrow has this kind of response to these gather filters, then maybe that means the eyebrow is raised, or if it has a certain kind of angle, then that means this kind of expression. So basically, once you have those features that you obtain from facial landmark detection, you can apply more feature extraction after that on those particular points to do, again, more processing. So this is an example of detection of different action units, such as, I think it's AU6 on the left, which is smile, means a lip raise, and 9, I don't remember what it is, but in this case it's not activated. Okay. I will now give you a small introduction about CNN. So deep learning is a big buzzword right now. In object recognition, in images, it has really been a revolution, and it has completely exploded all the state-of-the-art, basically baselines in the previous years. And now every year, if you go to computer vision conferences, it's all about deep learning techniques because they're really much better than what we used to do. So one of the big picture ideas that I think we want to give you is that in deep learning, one of the great intuitions is that I introduced before many kinds of features that we defined, as engineers. We say, well, we're going to look at the response for this kind of image processing filtering. In deep learning, you let the computer figure out everything on its own. You say, well, here's an image, and now look at what's useful to detect a face. So, as I said, this led to really great improvements in image processing. Actually, the kind of models that I use are really not new. It's basic neural networks in most cases. However, the increases in data that we have thanks to maybe huge companies and huge data sets have made this available. So it's really a revolution of the available power and data. So the main tool for deep learning is convolutional neural networks. The idea of convolutional neural networks is you have different layers, one after each other, that do different kinds of processing. One intuition is that if you want to detect, football or in an image, you don't need to look globally at the image. You need to look at really local patches because it's going to be the same locally. If it's a football, anyway, if you look at the right side of it, left side of it, it's going to be similar. You don't need to look at the whole image and the whole features. You only need to look at local things. And then all these local windows where you look at, they have to use the same model because it's the same kind of football. So basically, one of the big advantages of convolutional neural networks is that they use very few parameters compared to previous techniques. You have first layers that try to look for very small features locally, and there are very few parameters. And then you add another layer with also very few parameters, etc., etc., etc. So, why different layers for object detection? one reason is that actually when you have a visual scene, you can organize it hierarchically. You can say, well, this coffee cup is on top of the table, which is on top of the floor. And basically, you can then organize your image in a way that you look at a hierarchy. You first look at, well, maybe I didn't put this right, but first I see corners, then I see the shape of a coffee cup, and then I see the texture of a coffee cup. And this is already in a hierarchy. Also, biological vision is hierarchy organized. When neuroscience has given us insights into how processing is done in the neural processing part of the brain, and actually your brain first detects very simple things like edges and contours and corners, and then shapes, then objects. So the idea of convolutional neural networks is to mimic this kind of layered idea. Also, why not use simple techniques for image detection? One of the great advantages of having these very small local models is the translation invariance problem. To give you an idea of how neural networks used to fail with this kind of very large object detection in images, is if you train a classifier on this kind of number images, and it can be absolutely great, with very common techniques like neural networks. If you have lots of images of an 8 and you center them nicely, it will detect an 8 that it's centered nicely. And it will say that this flag is not an 8. However, if you then have a very large image and you move your things in the corner, then your classifier that learned only centered things will not know that, oh well, I don't know where this is, there's nothing at the center. The idea of a convolutional neural network is to really look for smaller patterns in local patches of an image. So a kind of representation of this is, instead of looking at this whole image as, which is what we used to do with previous techniques, you just have very small patches. If you want to detect a baby in that image, you don't need to look, you just need to know that there's one here. You don't need to know that there's one here. And it's very easy, for example, to look at these small patches, that this is a patch of grass, and that this is a baby, and maybe there's a tree in the background. However, if you took the whole image, it would be very hard. So, for every kind of these very small town, you basically use a very small neural network that's used to detect a tree or a baby on a very small image. And you get an output array for every kind of these towns. Another idea in convolutional neural networks is that since if you know that a baby is, or a tree is very likely to be in one of these towns, well, you don't need to know that it's also, you don't have to look at the whole area. It's fair, you already know. So you can take multiple tiles and take just a vector results. If you have one tile where you really know there's a plane here, well, all the local area, you can say, well, there's a plane in that general area. What this does is that this is called max pooling. You actually reduce then the size of your array in the end. So this is just an introduction once again, so I don't want to go into too many details. So that's the idea of convolutional neural networks. You have very simple layers, one on top of each other, that do very, very simple operations. And at the end, you can add a classifier on top of this to perform the object recognition. If you're interested in this, we'll have more details on the machine learning classes. Final thing, small introduction about what the Kinect does and how you track body and gesture. Body information is actually quite hard to detect in images, and if you have depth data, it's much, much easier. So that's why the Kinect has become very, very popular, not just for gaming, but also in the research communities and art communities, because it's so cheap for a depth sensor. Depth sensors used to range in $1,000. And it's actually quite precise. You can very, very easily detect the skeleton. There's a freely available API, so you can get your skeleton in a matter of minutes. What are the main ideas? How does Kinect work, basically, to find the skeleton in different body parts? Well, it works on a frame by frame. There's no tracking. And it tries to take every pixel in the input image, the depth image, and to match them to a kind of body part. So this is, this is the hand, the arm, this is the calf, this is the knee. And a very big part of its success is that it uses a huge amount of data. And how were they able to do that is actually using synthesized data, so not actual data. So what they did in Microsoft, they actually used a lot of motion capture, so actual human data, but recorded with suits. I don't know if you guys know what motion capture is. So basically you have a suit with different trackers, and it's very precise. It's used in Hollywood to do very state-of-the-art animation movies. And so you get this really precise data, but it's really hard and expensive to record. But once you have it, it's there and it's great. So what they did is they actually took that data and they did what they call they retargeted it on different meshes, which is they took the skeleton data and they took different kind of body types and they created lots of animations. So it's like different people did that animation. And then they created the depth data for the synthesized depth image for this data. So this allowed them to use a lot of data, and this was really one of the most important factors in the success of their models. Then only very, very simple features are used for deciding something is a body part or another body part. It's actually features that look at the distance between two, they look at two pixels, for example, this one and this one, or these two. They try to see if they are on the same depth or if they are on a different depth. And basically then it's actually randomized decision forests that are used just on these features. And if, I don't know, you got a picture here, if on its left it's deeper and on its right it's on the same size, then maybe it's likely to be shorter. That's just an intuition of this kind of decisions that are made. Really the important point here is that they were able to have so much data that this system could produce very, very high accuracy. Okay, so that's it for today, I think. I will present the homework now. I think it should be on Blackboard. Are there first any questions on these algorithms or the second part of the course? Yes.
Yes, about the segmenting people from the Kinect data. Do we have some kind of data to evaluate how good the segmentation is? I mean, what part is the human body and what part is not?
Well, there are publicly available datasets with Kinect data. The problem with Kinect data is depth data can be very huge. If you record some Kinect and it takes the raw data, 1 minute is maybe, I don't know, hundreds of megabytes, I don't know, maybe even a gigabyte. So very, very fast it's become hard to do. However, it's very, very easy to record your own. The Kinect API is extremely easy to use. And we have something I will present in the next course, which is called Multisense. Maybe we already talked about it, which is a software we developed at the ACT here. And basically in that software there is a recognition suite and a recording suite. And if you have a Kinect, or we can provide you with a Kinect and you want to play and try to recognize things, you could get your own data in this way. So you could evaluate how good this is maybe. Yes?
So, to use the convolutional neural network to detect facial expression, do we just feed in the raw data? There's no image processing anymore, or still there's some feature extraction?
Well, the big idea here is usually it's all the feature extraction. You let the algorithm decide what are the best features. And in a sense, there are some interesting papers that maybe we'll make available to you that try to look back at what features the convolutional neural networks look at. And when you train CNN to detect facial expressions, what you see is that the first layer really detects edges. And the second layer detects corners or contours of different things. And then as you go up in those layers, you detect more and more complex objects. Also in the object detection application used, for example, for Google Images, they have lots and lots of different objects, and they share the same underlying layers. So you have very, very general layers for edge detection first, and then as you go through, you get these complex images that can be used, for example, in the case of facial expressions, they will, the more higher you go, they will start to resemble, I don't know, a raised eyebrow or a lip. I don't know if that makes sense, but the big difference, and I think the big intuition of deep learning is that you don't yourself as an engineer or researcher say, this is the kind of features we're going to use because we know from psychology this is what's relevant. You let the computer do everything on its own. And in a sense, that's why it gets so great results, because it really optimizes what an image looks like. I don't know if that answers your question.
Isn't that a bit frustrating for researchers?
I think maybe it has been frustrating for computer vision researchers because they spent 30 years on designing those features and saying, well, yeah, that was a huge part of the whole research field, saying, we found a great feature. Also, we had a lecture on speech analysis last time. I don't know if you remember the MFCC, the male frequency substrate coefficients. So those are, you know, a bit involved, a bit complicated, and they're very useful. They work really well. And then deep learning comes in and crushes your results in a second. So yeah, it's probably a bit frustrating. I don't know. But in a sense, it's great that it works well. So. Okay, maybe I'll present the homework now. Okay, I don't know if it's available yet. So, first. So the first homework you have to do is a kind of YouTube sentiment analysis, and I think that will give you a sense of the kind of things we expect from you for the project. So the first homework, so there are two parts. It's the same homework in a sense, but we split it into two. Will be due at the end of the month. So there's a data set. There should be a link here, actually, for you to download. And it's a set of YouTube videos. You can see a link here. There's a link. So it's about 1 gigabyte, so download it early maybe. Your task will be to basically look at these videos and try to notice what kind of behaviors you see, what you think is relevant. And we've added in the data sets already annotations of different behaviors and extracted features. So the first part, the first data set is really more like a descriptive kind of work. So we'll have to look and make hypotheses and try to validate them with machine learning and statistical analysis. Next week's lecture is on machine learning, so you'll have basically some background on that. And it's really more about getting acquainted with this data. You know, we'll have to plot maybe histograms of different action units to try to see, I don't know, maybe do females smile more? Is a video where the person smiles more, is it more popular? Does it get more likes? More thumbs up? Right. So everything should be on Blackboard. If it's not available, I'll make it available very soon. This is to be done individually, not like your project. And yeah, I think that's about it. Everything should be there. Don't hesitate to send us questions if you have. On the topic of the project, so your draft project proposal is due next week, Friday, I think. So I hope everybody has a group more or less, so 4 to 5%, right? Okay. Well, so it's just a page. We just want to. We do not judge yet. We just want to see if you're really going too ambitious or not ambitious enough. This kind of thing. Is there anything else? Yeah, I think the data set should be described here. Let us know if you have any questions.